The following recording is a Somali Society of Engineers presentation conducted on May 24th, 2026. Our presenter today is Engineer Abdikarim Ibrahim. Abdikarim Ibrahim is an aerospace engineer with expertise in propulsion systems, flight sciences, and GNC, guidance, navigation, and control. He holds a Bachelor of Science in Mechanical Engineering and Mathematics and a Master of Science in Aeronautics, Astronautics with a concentration in GNC. His technical background focuses on guidance of autonomous systems, flight dynamics, navigation, and advanced control systems design. Professionally, Abdikarim works as a propulsion systems engineer at Boeing, where he supports the development, testing, and certification of the GE9X engine, the world's most powerful commercial aircraft engine. His work spans propulsion, engine integration, flight testing, systems engineering, and next-generation aerospace technologies.
Well, hi everyone. Assalamu alaikum wa rahmatullahi wa barakatuh. And thank you, SSE, for the introduction. I am Abdikarim Ibrahim. This session is about, we can't really talk about all of aerospace in one session, but we're just going to scratch the surface and talk quickly about if you are a student, what areas you should expect to end up. If you are looking to get into the industry, what opportunities are out there? Do you have to have a bachelor or master's degree to be working in the aerospace industry? All of those questions will be answered, hopefully. I'll do my best to answer all of those questions. But first and foremost, I want to get some introduction out of the way, including this disclaimer. I try to keep the originality of the template that you guys provided, SSE. Thank you for the guidance. And everything I show or share today is my own experience and perspective. If you have a different experience in the industry, that is also welcome, but I'm just sharing my own experience. My name is Abdi Ibrahim again. I graduated college in 2021 from the University of Washington. I have bachelor in mechanical engineering and mathematics. Most people do not like math, but I enjoy it, and to the point I did it as my minor. I am also 2 weeks away from getting my master's in aeronautics and astronautics. My area of expertise or area that I focused was GNC, or guidance, navigation, and controls. And some of my professional backgrounds is currently I'm working at the Boeing company. I'm a propulsion systems engineer. I work both design of the propulsion and engine controls design, as well as the testing and fire safety side of the engine. I've worked on 737 engine last year and the year before. And this year, we're working on 777 engine. The GE9X is to power an airplane that's currently under development that's supposed to enter service in 2027. And it is about to beat the largest commercial airliner in the world. That is the A380. And so 777X will be the largest commercial commercial airplane in the world. And so because of that, it needs an engine that can withstand the power and the mighty of that aircraft. So currently, we're working on the certification process for the GE9X. I'm currently in Ohio, and that is where the engine is developed, tested, and certified. Prior to Boeing, I worked at Blue Origin, which is a space company owned by a guy named Jeff Bezos, who, in a way, probably had some effect in your life. He's the guy that started Amazon and made so much money that he wanted to explore space as well. And so I worked as a vibration and dynamics engineer on their rocket developmental developments. It's called BE4 engines. They are powerful engines that power their human transport rocket, New Shepard, and New Glenn, which is an orbital rocket. But I needed a transition after a year because of graduate school. Blue Origin is a very good company to work for, but as a student, Boeing actually offered a better deal to study, pay for my school, and at the same time have a full-time job. Right out of college, I started my first position at Textron Aviation as a actuation systems engineer. I worked on the landing gear systems for Cessna airplanes and Denali airplanes. And this is where I really, truly learned most of what I have applied from the next few years. But we need to start with a question to hopefully gauge your knowledge for the field. And so, anybody know what the four forces that apply to an airplane is? We can take a minute. You can type it out. You can say it out loud. What
I think I
are
can
the
say two
main
of
forces?
them, gravity
Sorry,
and also the wind force and gravity. I think those
gravity
two.
and wind. What else?
Thrust.
Thrust. That's a good one.
There's
Not
four forces acting on the space and airplane والتراست إدراج weight and lift.
There you go, Mahmoud. Thank you. Yep, absolutely. Those are the four forces. Everything we design on an airplane or a rocket, we're basically trying to balance those four forces. You have thrust produced by the engines or propulsive force, and countering that is the drag. It is the resistance that comes generated by the airflow around the engine or by the airplane or the rocket. And then we have a natural force, gravity, that applies to everything. And then we have a lift generated by the wings. Lift is you get it if you just get it the right design. If you don't get it, then you don't get it. You probably crash. So those are the four forces, and everything aviation is about balancing these forces and making sure that you can make flight possible by controlling and balancing these forces. And we'll see a little bit more on that. We'll get deeper into this, but let's go through and see what the screen is getting stuck. There you go. So aerodynamic forces, as you mentioned, is lift versus weight. So a lift is generated by the airflow over the top of the aircraft or over the top of the wings or under the wings. As air flows through over the wings, you have a low pressure air at high velocity at the top of the wing, and then you have a low pressure, high pressure, low speed airflow under the wings, and it's that pressure differential that generates the lift. That phenomena is called the Bernoulli principle. There's also another theory that exists to explain that, what's happening, and that is Newton's third law. Basically it says, it's equal and opposite reaction forces. Basically, you have a low pressure air trying to put high pressure air that's trying to push the aircraft wing up. And then you have a low pressure air at the top that cannot resist that amount of force, and therefore you generate lift. Which one is correct? It's for scientists to debate. I'm an engineer. I care about what works. So I take whichever works. So today's agenda, we're going to look at a few things. We're going to define what aerospace actually is for the students and people who are trying to get into the industry. And then we're going to look at the core aerospace disciplines. What areas of studies should you expect? We're going to look at the design process, testing and certification process. I'm a developmental engineer, so I don't really look at manufacturing or production, but that's also two other areas that exist. And then we're going to look at the careers in the industry. When I talked about, can you have a career in the industry, whether you are an engineer or a technician or a supply chain professional, anybody can be in this industry. And that's what I'm trying to convince you all. So what is aerospace? As you can probably tell from these two photos, one on the left is a fighter jet. It's a fourth generation fighter jet. And aeronautics and astronautics is the two divisions of aerospace. Aeronautics is the study of things that flow within Earth's atmosphere. Astronautics is things that go to orbit and higher, that go beyond Earth's atmosphere. For aeronautics, it is the study of the airflow. We're talking about the four forces we talked about earlier. Is a study of those forces, and it could apply to airplanes such as helicopters, gliders, drones, high-speed fighter jets, and it puts a huge emphasis on drag, stability, propulsion, performances under atmospheric conditions, and that is aeronautical engineering. It does apply into fighter jets, commercial jets, and so many other things that fly within Earth's atmosphere. For astronautical engineering, the picture on the left kind of sums up. It is the science and the study of rocket launch. Why are we able to escape the Earth's gravitation? That study is done under astronautical engineering. It is the flights beyond Earth's atmosphere. It puts a huge emphasis on rockets and satellites and space probes and managed spacecrafts. Once you leave Earth, coming back to it is called reentry, and the physics of that changes completely. You have to deal with thermodynamics, you have to manage heat, you're dealing with radiation, all that stuff. And so it's the study of getting things into orbit. What are the fundamentals of flight? Like I said before, balancing the four forces we talked about earlier today is about getting a flight out from the ground. Lift versus weight, thrust versus drag, and control comes from managing these forces. You can have a very high-speed aircraft, but if you can't manage and control where it goes, then you're just going to crash. So making sure that we can control an airplane or whatever we are designing, rocket, is crucial. Not only do you have to get the forces right, but you have to also get the control inputs correct. Some of the core disciplines that are studied as a student, you could be studying aerodynamics, you could be in propulsion, or even an engineer. You could be an aerodynamics engineer, you can be a propulsion engineer, or you could be a structures and materials engineer, or you can be a GNC engineer. The design and tools and things like that are used for the design of the four things above will be also shown today. Aerodynamics is one of the most important things, or one of the most important phenomena studied in aerospace. It deals with the airflow over a body, whether that is an airplane or a rocket, and it puts a huge emphasis on lift, drag, and thrust, and gravitational forces. And it uses principles like Bernoulli's principles and Navier-Stokes equations to describe how air flows over an aircraft wing. As you can see from the middle section, middle photo, you have a commercial aircraft flying, and then you have an airflow coming to the plane. At the leading edge of the aircraft, you see that air still sticks. We absolutely want that. The reason is, if you don't have that, what you have is something called separation, and separation creates a whole lot of problems. It increases your drag. You're basically no longer fuel efficient. You can lose the speed, and you can lose altitude if you continue long enough. And so we want nice laminar flow over the top of the wings. For a fighter jet is a different physics, because fighter jets have a pointy nose. They are trying to cut through the air, and effectively what's happening around the aircraft is a turbulent flow. You can see the air is no longer smooth, and the way they work is just different. They have a rocket mounted to the back of them, and therefore they don't really care too much about the engine, because the engines are not mounted to the front of the aircraft. The physics of that is a little bit different. And then the four forces we talked about earlier today that we're trying to manage is any flight that is flying around the world, these forces apply to it. Another area of study is propulsion, specifically propulsion thermodynamics. This is my area that I currently, my current work area, and it is the study of changing heat into a mechanical energy or mechanical work. It is to produce thrust. And what's happened in a jet engine is you have a large amount of airflow coming through the fan case. That air gets compressed. And by compressing the air, you're also increasing its heat. And then that compressed air and high temperature air is then fuel is added to it and then ignited. And all of that massive hot gas is pushed out through a very small nozzle out in the back. And effectively, you are creating a propulsive force that pushes the aircraft forward. And that is propulsion for you. For a rocket, propulsion is slightly different. For airplanes, because they are flying horizontal, you have four forces balancing each other. And as the airplane propels through the runway, it gets up to a speed called takeoff speed. What that is when the engines produce enough thrust for the airplane to take off, and therefore the wings also generate the lift, and that's how you have a flight possible. For a rocket, it is a vertical lift, so the forces apply differently. Same ideas, just differently. You now have your drag and your gravity pushing you down, and therefore your thrust from your engine has to overcome those two forces. And rockets have to reach something called a maximum velocity called escape velocity. It is the maximum velocity needed to escape Earth's gravity in order to put something in space, satellite, whatever, what have you. Aerospace materials, they're everywhere. Picked A330, even though I'm a Boeing guy. But I love everything that aerospace related. Materials in aerospace is to understand and identify the most suitable and most efficient material for any design, making sure that it is lightweight, it can withstand the heat, it can withstand the structural loads. We're trying to get the best possible materials for any design. For structural dynamics, we're trying to make sure things survive, for example, engine vibration or turbulence. You're flying at 40,000 feet altitude and you hit turbulence. Is your aircraft able to withstand those turbulences? Those are, how do we know? How do we find out? We test the airplane and every component in a lab to make sure that every component on that aircraft can withstand what it is designed for. And then we have another area, GNC, Guidance, Navigation, and Controls. This is the area that I've been studying for the last 2 years in graduate school. It has three main areas, and those are stability and control. That is a whole group within Boeing called SSE. They do the most exotic tests you will ever see. They fly the airplane and they do zero gravity. They do nose dives. They test the airplane's limits to make sure that airplane, if it's in a condition where it's a nosedive, we can recover the airplane. And they just create a crazy flight profile and follow it. And these are the guys that test the airplane to make sure that it is safe for human flight. And the pilots that test these kind of airplanes, like test airplanes, they're not real commercial pilots. They are trained test pilots, usually with a military background, and they can survive like crazy maneuvers and stuff. So there's a whole group that does stability and control testing. And if you are an engineer in that area, you'll be part of that group doing stability and control testing and design as well. Flight control systems are people who design the control services. Autonomy and navigation are people who design the aircrafts, literally the airplane brain. They design how the airplane trajectories, the GPS, all of that stuff, communication systems. These are the team that designs that kind of stuff. Stability and control. There are two things that we worry about as in stability and control, and those are static stability and dynamic stability. They both of them are designed around a disturbances. So, for example, you're flying and you hit like turbulence. How long does it take for your airplane to recover and come back to equilibrium or level flight? The statics and dynamic stability study those before we even take off a flight. One of the things that is very crucial in airplane design is understanding what the center of gravity of an aircraft is. If you don't know, basically, if you are designing a small airplane, one way to test it is put it on your finger and see where the balance is. That is your center of gravity. If it is towards the nose of the aircraft, well, that's your center of gravity. If it is towards the tail section of the aircraft, that is your center of gravity. Center of gravity is not about the length of the aircraft. It is about the weight of the aircraft. Where does that happen? You probably have heard about the 737 MAX crashes. That was where they messed up. They messed up the center of gravity right there. And it's fixed now. It's safe aircraft, but the main story was center of gravity. Where they mounted the engine on the aircraft was the biggest problem that made the airplane crash. Sad story. Let's push through. Flight control systems is, like we said, is the control surfaces. Remember, airplanes don't have a steering wheel like your vehicle. They use flight control surfaces to turn left, right, roll left and right, to pitch up and down. These control surfaces are pretty much your steering wheels. For example, your elevator gives you the pitch up and pitch down. So when you're taking off, there's an angle of attack requirement. That is the angle between the aircraft nose and the ground. And that angle of attack should not exceed a designed angle of attack. Otherwise, you're going to stall and crash. So elevators is a way to control that. Ailerons give you the roll to the left and right. For example, when you take off from an airport, you can watch this. When you take off, the airplane will just bank to the right or to the left, regardless of wherever it's going. The reason for that, why don't we just take off into the direction we are going? Typically, that is dictated by the wind direction. You always want to take off towards the wind because it helps you lift. And so after that, you can turn and go to the direction you are going. One of the ways we can do that is ailerons, and they are on the wings. So if you drop your left aileron, you are doing a right turn. How about if you want to just be stable and just yaw to the left or right? These directions have specific names. It's roll, it's a yaw, it's pitch up and down. So those specifically flight control surfaces are why you're able to make those type of maneuvers. This is specifically from my grad school research. I've done this. It's a flight simulator. It's a full flight simulator. And what we're doing here is, give me a second. I'm not sure why my screen just disappeared. So basically what you have here is you have this, before you ever fly an aircraft, you have to understand that how the flight control system behaves. And so you have a pilot input, how the airplane reacts to specific control inputs. So you can have either a static input or you can have a dynamic input through a joystick. So if you are a pilot flying a remote aircraft, you probably are using a joystick. And because your hand is not steady, it's going to somehow not going to give the aircraft the perfect inputs. Or you could just provide the aircraft unknown inputs and then see how it behaves. And then the system processes your inputs. It calculates your angle of attack. It calculates your rate of speed, the rate of change of speed. It calculates a lot of those phenomena that you're looking at. And it can display I have another screen that's coming, but you can display and look at and visually look at how the airplane is handling according to your control inputs. There you go. So that flight simulator we just saw, I have inputted or uploaded. There's a software called Explain and another one called Flight Gear. So this one right here on the left side is Explain. Explain has a whole bunch of airplanes where you can test your flight controller on it or your simulator on. It's a virtual airplane, and you can upload and integrate your controller into an airplane and just literally fly at your own desk using the joystick we talked about right here. So this is a Boeing 747-400. It's one of my favorite airplanes, and I have tested my controller with this airplane. The airport I took off is my current where I currently work. It's a Boeing field in Seattle. As you can see in the background, there's the famous Lake Washington in the Seattle area. And so I'm still not level. I'm not a pilot, obviously. So I'm still trying to level the aircraft after takeoff. That's to be expected. And and I'm also visualizing how the airplane is responding to my control inputs. Down here is a Cessna 172, I believe. It is from Flight Gear. It also has smaller airplanes, and you can also you could just ignore your controller and just pick any plane and fly and just test your handling qualities. And so this is Cessna 172. I have modified the geolocation of this location to put it in somewhere in Somalia. This is actually Beledweyne, Somalia. As you can see underneath the airplane, that is the Beledweyne, the river. I think that river is called Genane or forgot the name. But I'm flying over I'm flying over Beledweyne of Somalia.
Abdikarim, are you sharing the slide that says MATLAB, or you share another screen, slide?
Sorry, I'm sharing. Do you not see my screen?
You're sharing the one that says MATLAB and Simulink.
Yeah.
That's the one you're sharing. Okay.
Yeah, that's the one I'm sharing. So I wrote MATLAB and Simulink to show that it is what I used for this type of flight controller design. It was MATLAB is for the programming and Simulink for the graphical representation. You can use Simulink is used for control design, and LabVIEW is also another one that's used. But for the most part, I used MATLAB and Simulink to accomplish this. How about navigation systems? Navigation is about providing the aircraft a real-time data about its position, velocity, and heading angles. It is to understand where in the world the airplane is in the aerospace, and it is crucial for stability and safety and mission execution. If you have 200-300 people in your aircraft, it becomes a mission to make sure you take off and land safely. This screen on the left shows you that your airplane is either level or not level. So when your screen is, it's got blue and red or coffee-ish. So that is to show you your airplane is level flight. If it's not level, then you have a problem and you gotta correct. Sometimes that screen is not, it's not always like that. Sometimes you're doing a calculated turn and your screen is going to be different. And here is where you display all the objects in the aerospace with you, other airplanes, helicopters, or things that are within the aerospace will be displayed in your navigational screen. Airplanes use satellites to get the data they need to understand where they are in the world. Global positioning system, apparently that's also used in airplanes, not just for your phone or for your, on the ground. And so they use GPS satellites to calculate objects' position on Earth. It works by receiving a signal Sometimes, depending on where that satellite is in the globe, there is a delay, and that delay is pre-calculated into the data that you're receiving or the signal you're receiving. If you're driving a vehicle and that delay is taken out of the calculation, you will miss your turn. And so there's about 8-second delay that they take into account. It takes about 8 seconds for a signal to leave Earth and hit a satellite and come back down. It takes about 8 seconds. So that 8-second delay is pre-calculated. And so what you're seeing on your phone is it is the real data minus the delay. For airplanes, we use something called INS, or inertial navigation systems. There's a variety of them, but the ones that specifically airplanes and rockets actually use is a gimbal system. And so if you want to picture your face, you're looking at it like you're looking north. And if you turn your face and your eyes is basically always fixed to the north, that's kind of how it works. I can't really explain it, but that's kind of how it works. It's like a system that has a frame of reference that it's always, no matter how the airplane turns, left to right, it doesn't matter. This gimbal system always has a frame of reference. That's typically the Earth's magnetic that is used as a reference. Some of the tools that are used in the aerospace, specifically simulation tools. If you are a fluids person, you probably will be using CFD, computational fluid dynamics. If you are a structures person, you'll be using FEA or FEM, finite element analysis, and so many others. ANSYS does a lot of, it can do both actually, and plus more. ANSYS, you can use ANSYS to understand electromagnetic interferences, why you're told to not make a call on in an aircraft. Is one of the reasons is we're trying to understand the electromagnetic interference, because when you are on the phone, you're communicating with satellite, but so is the airplane. And so you can have interference with the airplane communication system. And that's why it's federally illegal to make a phone call mid-air or even during takeoff. So if you're a student wondering what sort of tools will I see in the industry, this is just to scratch the surface. LabVIEW is one of my favorite softwares, and it's used to do graphical designs as well, just like Simulink and MATLAB. Conceptual design, typically a design is driven from either a customer request or a company does a market analysis and figures out they need a certain design added into the market. For example, Boeing 737 MAX came from a competition standpoint. Airbus basically designed an A320 aircraft, and it was selling like crazy. And Boeing said, you know what, we're losing to this company. We have to come up with something fast. And that's not the safest way to design an airplane, but 737 MAX was born because of that, to counter Airbus. And so typically you come up with initial design and it goes through process and years of development and testing. And but the conceptual design can either come from a customer or it can come from a market analysis done by really rich company like Boeing and Airbus. Because you can't just say, hey, I think the market wants this kind of airplane, and you go ahead and design. If you are in a small airplane, manufacturer, you can't do that. You need a real request from a customer. What kind of customer will drive or generate this type of design? Big airliners like Airbus, for example, Emirates Airlines, Lufthansa, Alaska Airlines, or domestic U.S. airliners usually are the ones behind driving smaller airplanes. So, for example, if you are a Boeing, for example, and you have 777 that can carry 400 people, versus you have a 737 MAX, which I think goes up to 300 people or 250 people, but you want something in the middle, then you can say the market needs this middle market aircraft, or you need a smaller jet, like a business jet, there's a whole department called Boeing Business Jets, and that is to design for rich people and people with money who just want to fly themselves. So conceptual design comes from either a customer or it comes from a competition standpoint. But typically, some of the processes that we go through is what kind of range are we looking for? If you are designing for an airliner like Emirates Airlines, you're looking an airplane that can travel across the world without refueling. So your range is a big deal. Payload, what kind of payload are we looking at? What kind of speed? Speed is big deal because you can either design for Mach 1, or you can design for Mach 5, which is a fighter jet. So high-speed airplanes. If this is a military, we're talking about speed defines what kind of airplane you actually design. So if a military comes to you and says, hey, we need a 5th generation fighter jet that can do this and so and outmaneuver the hypersonic missiles around the world, then your speed changes, your whole design changes, a lot of things change. And also regulations is a very important thing. I'll talk about why regulations matter later, but US Aerospace has its own regulations. Chinese aerospace or authorities have their own regulations. EASA, which is the European Aerospace Association or Aviation Association, they have their own sets of rules that every airline manufacturer or aircraft manufacturer has to meet. And then Boeing FAA, if you want to fly in US aerospace, you have to meet their requirements. And typically we come up and we come up with a final design. We basically come up with a mission profile, and we do the system configuration. We chose the airplane, so multiple configurations are initially designed, and then we basically rate them based on meeting the needs at hand. We look at estimated, we look at weight, size, we look at engine power or what's needed, what kind of engine is needed, and is that engine in the market already, or do we have to make a whole new engine for this new airplane? Usually, engine is a big decision early on, because if you have to develop a new engine, you're basically developing something like an airplane. So having an engine available for your chosen aircraft is a crucial step in the design process. And basically we now have a baseline design. So that's how a design process usually goes. FAA and testing and certification and what goes on. There's a variety of things that needs to be done. Testing is done for specifically to meet requirements and for safety. You can't put something that's not safe. There's a huge emphasis on safety in aerospace. And if you're not someone who has safety in mind first, then you're not going to be, I'm not going to say you're not going to be successful, but you're going to have a problem, really. Safety is huge. It's a big deal. And so there are a variety of tests that are done initially to identify the weaknesses of your design. One of them being wind tunnel testing. This is where you introduce the aircraft, the most extreme conditions of aerodynamics that airplane can face. Turbulence, high winds, all kinds of stuff. And you understand how the airplane behaves based on those inputs. Propulsion testing, if you have selected an engine for the aircraft, you obviously need to do an engine testing to make sure it meets your own requirements. Flight testing is after we have done all the structural testing and every component on the airplane has already been tested in a lab. You put together and you do the flight tests. Structural and vibration testing is also done early on before flight test, and that is typically to expose all the the weaknesses on any specific component on the airplane, and so on and so on. There's fire testing, there's chemical testing, there's EMC and EMI testing. All kinds of stuff are done to make sure that this airplane is absolutely safe for human, to carry passengers. Wind tunnel testing is one of the most crucial, as I talked about earlier, and it is to basically you build a small model of the airplane, you put it in a wind tunnel testing, and you're generating the conditions that the airplane will be flying generally by, blowing a high-speed air on the plane and seeing how it basically behaves. You're looking at the airplane aerodynamic performances. Things like lift, drag, and stability are studied here. Angle of attack. What's my takeoff speed that I need? What angle of attack do I need? These kind of stuff are calculated, pre-calculated, and it's not like a known numbers for every aircraft. You actually have to do wind tunnel testing to understand what each aircraft requires. Wind tunnel testing is also to support static stability. Is the airplane takeoff and landing stable? What about if disturbance happens to the airplane? Is it still stable? Can it recover from disturbances? We're looking at all those things. And so wind tunnel testing is crucial. And I think there are 5 or 6 wind tunnel labs in the world. This one is from the University of Washington. And then there's one in Seattle, there's one in Charleston, and there's one in the UK, and there's one in Japan. There's that many. And I think Airbus has one. So there's about 5 to 6 of them in the world, because they are very expensive to build. They do require jet engines to produce the wind speed needed. Propulsion testing, this is if someone asked me what I do, this is what I show them. This is what I do currently. This is from last year. This is 737 LEAP 1B engine. And you might ask, 737 has been flying for years. Why test last year? Every time you redesign the engine or add something to the engine, it triggers a recertification of that engine. The 737 engine had a system added to it called RBS, reverse bleed air system. And what that system does is after the engine is shut down, it collects all the smoke residue from the engine and exhausts it out. What that does is it increases the engine service life by about a year. And that is a big deal in the industry because engines are very expensive. And as soon as you do that, now you trigger all of these certification requirements. Are you still certified for fire extinguishing? Can you still put out fire because you added new systems? Are your airflow still the same? All of that stuff, it triggers a whole new certification list. The one on the right is GE9X engine. This is currently what we're working on. It is massive. You can fit the 737 engine through the GE9X engine. It is so massive that you're standing next to it and it's a plane. It's literally a whole plane. And so there's a lot of stuff that are done in this facility here in Peoples, Ohio, but the specific area that I currently deal with is fire safety, is making sure that if engine fire happens, we can put it out. FAA has a requirement. It's not just FAA, it's actually EASA of Europe, the Chinese Aviation Authority, FAA, they all have a requirement. And I think it's a global thing. Engine fire has to be needs to be gone within half a second. You detect it, half a second, gone. And because there's a large amount of air flowing through it, whatever you expose to the engine, it's just going to be shot out in the back. So you have very limited amount of time to put out that fire. Why half a second? Because there's fuel going into the engine that can add to the fire, and therefore the whole airplane can catch fire. And that's why it's really, really important to put it out quickly, as quickly as possible. There's a quick video that we'll come back to, but I'm going to finish my thoughts here. Propulsion testing. Why fire testing here, and how is it done? 9X engine. This is my lab hardware. What we are doing here, this stand you see here is you're simulating an aircraft wing, an engine mounted to it. And as you have probably guessed, you do not use water to put out fire on aircraft because of weight. We're saving weight. So we have to figure out another way to put that fire out. And one way is using a chemical called halon 1301. It is in a compressed gas. It's a compressed gas. It's especially designed pressure vessel, typically installed on the aircraft wing. And what we're trying to do here is mimic a production engine. And so we discharge the bottle by applying voltage to it. It's a little bomb. It's an explosive bottle. And so we discharge the gas to the engine, and the gas rushes into the engine, and engine has specific areas of concern where we like to target. And then we measure how long it takes for that engine, how long it takes to reach the concentration we need. There's a pre-calculated concentration that we are looking for typically, and we want to make sure that we are able to reach the concentration within half a second. How do we do that? We do that by instrumenting the engine with copper wires or copper tubes. The copper tubes is basically instrumented and placed in the area of concern, and they are open. They're open to both sides, so it's like a tube, and you basically take a sampling gas. You're sampling the gas within the engine after you discharge the bottle, and that gas is then fed into these transducers under the engine. The transducers are gas analysis transducers, so they can measure the concentration. That concentration is then run through a bunch of cables, signal cables, that run on the ground and go into the control trailer where we typically sit behind these barriers. These barriers are for our own safety in case of engine fan blade out or things like that. Anything can go wrong here. So we have to make sure people around the engine are protected. And then that concentration is transmitted as a signal, as a voltage signal, and then it gets displayed on a nice little screen on our control trailer, and we can calculate the concentration and determine whether we have met the required concentration levels or not. I can tell you from experience, it is one of the hardest tests in aviation to pass because of when you discharge your bottle, your gas distribution has to be so precise in order to meet that requirement. And so the nozzles and all the nozzle designs that go into it has to be so precise. Your nozzle diameter, your nozzle length, your nozzle bend, everything has to be just perfect in order to meet that requirement. You have no choice. You cannot fly this and certify this engine without meeting that requirement. And so I want to show you a quick video of where this is done and how this is done. I'm going to try to share my screen one more time here. Can you see the video?
No, sir.
No problem. Okay, let's see. All right, I'm gonna come back to it actually. Let me see. I'm gonna stop sharing real quick. Oh, there you go. All right, welcome to Peoples, Ohio. Can you hear the sound?
Oh no, we cannot hear you.
Sorry, can you hear or not?
We cannot, yeah. We cannot hear you.
Oh, I guess there's a way to share the sound. I'm not gonna have time to figure that out right now. I'm gonna stop sharing and then show you maybe another one real quick. So that's more. I'll figure it out later. How about we continue with the presentation? Let's see. Let me try to reshare. Do you see my screen now?
Yes, sir. Yep.
Okay. I'm using two different screens and I am struggling to continue with this. So I'm just gonna disconnect it. All right, so that is propulsion testing. This is not just the only testing that's done. Typically, we also do something called acoustics testing. There is a sound and noise requirements in the United States that airplane have to abide by when you're taking off an airport. Your engine noise has to be within certain dB because of the neighborhood and people in and around the airport. And so we test to make sure that engines meet those requirements. And now let's talk about careers in the industry. If you are an engineer in the industry, you're looking at multiple roles, specifically if you're an aerospace engineer. By the way, I want to say that it's not just aerospace engineers that work in the industry. I have mechanical engineering degree as my background, and I still ended up here. I have met people with civil engineering degree, electrical engineering degree. So regardless of what you study, your degree doesn't matter once you end up in this degree, in this industry, because you're going to find something you like and you're just going to run with it. So I wouldn't worry too much about what you study. I think you should get more experience and get out there and do more tours on the kind of companies if you are a student, and figure out what you might like and just study that. Don't worry too much about should I study aerospace or mechanical or I wouldn't worry too much about those. But if you are in the industry, you could still be a mechanical engineer and be doing aerodynamics testing. You could be doing structural testing. Specifically, it is 70% mechanical engineers who do structural designs and testing. Systems, propulsion engineering, flight controls, and GNC systems engineering, structural engineering typically design the airframe, and they worry about fatigue and life cycle of the aircraft and components. Avionics engineers are mostly communication and electronic engineers. Test engineers apply to all of them. A test engineer could be working for any of these different fields because and I'll tell you one more thing. It is one of the most rewarding careers out there. If you are a test engineer, you are the person that's proving things right or wrong. In aerospace, we use three theories. Say it, do it, prove it. Say what you want to design. So that's where initial designs come from. And then you do the manufacturing by you doing it, and then you prove it by testing. The test engineers are basically the people who stamp the final say of any design. So if I was to give someone an advice, this is what I do. I would advise them to join me. Other technical roles that are not engineers. We're talking about aircraft technicians and aviation and aerospace overall technicians. They are the heroes of the industry, if you know what I mean. Heroes. You can fly into any airport in the world at 3 a.m. and there are mechanics standing there to inspect your airplane and make sure you have a safe flight next time you fly or next time that airplane flies. They work in a variety of different areas. They do engine testing, engine inspection, and they do component replacements. Aviation maintenance comes from fatigue life cycle. Why? When an aircraft component is designed, it is also designed to expire at certain point after many flights. For example, a landing gear. A landing gear can only do so many flights because it's taken all the heavy hits of the aircraft. And so it has to be retired at some point. And what happens when you retire it? You have to replace it, aviation maintenance. So these guys do hydraulics, landing gears, flight controls. They do all kinds of stuff. Testing, there are aviation mechanics, and they're not only working in aviation, they're also working in space, in NASA, they're working at SpaceX, they're working in car manufacturers like Tesla and what have you. So they are one of the most important people in the industry. And to give you a career roadmap, there is about 25,000 airplanes flying every day across the world. That number is about to increase to 35,000 airplanes per day by the year 2030. All of those airplanes require aviation maintenance and people who actually understand what airplane maintenance is. It is one of the most rewarding careers out there. And guess what? They are one of the highest paid people in the industry out there. So if I was to give you an advice, if you don't want to do a 4-year engineering degree, this is what I would tell you to do. Other key roles in the industry, it's not just engineers and mechanics. There are supply chain and finance and HR and project managers and IT and cybersecurity roles. And all of these combined make up a flight possible. I specifically wanted to talk about this role, aviation maintenance and power plant, because a lot of people actually asked me about it, and I wanted to talk about it just a little bit more. This is a licensed program by the FAA. It is a 2-year program and I have listed all the schools, or not all the schools, but some of the schools that provide it. But if you don't want to do 4 years, or you just want to switch careers, it is one of the most important ones. And this degree, you can use it anywhere in the world. You can go to Somalia and be doing this, because actually there is a lot of need in Africa right now for this role, because we don't manufacture the airplanes, but we use them, and we need people who can actually service the airplanes. So very important. There is 2 types, but I would recommend you get both: airframe systems and power plant. Airframe typically deals with structures and hydraulics and avionics, and power plant deals with power, engine, fuel systems, propulsion, things like that. And it is crucial. It's FAA certified. US government is giving you a certification to work on airplanes. That's really cool. And it is highly in demand. The demand for aviation maintenance technicians will continue growing forever. We cannot replace it. AI is not one of the jobs AI is going to replace in the future. I guarantee you that, because AI, you can only train AI so much, but these guys, they figure things out themselves. What schools can you find from this program? In the United States, I've gone ahead and listed few schools. I haven't gotten all of them, obviously, but if you live in Seattle, South Seattle College has a little airplane in the lab where you can actually just learn the theory and apply on the plane. It's very cool. And by the time you graduate, Boeing actually donated a plane to this college and said, go ahead and train people. And so by the time you graduate from this college with the 2-year degree, Boeing already knows you. And then you get a job. You get hired immediately after. I had a friend who went to school here, and him and I wrote his resume in 1 hour. And the first job we applied, he got it. And so it's very important program. In Minnesota, Midwest, and Central, there are also some schools that provide this. Lake Superior College in Minnesota, Pittsburgh Institute of Aeronautics, Minneapolis Community College and Technical College, Minneapolis Community and Technical College, and Northland Community and Technical College in Minnesota. In the East Coast, Embry-Riddle Aeronautics, University of Florida and Arizona, and National Aviation University. All of these schools actually do provide this program. It is 2 years, and because it's a trade school, most states will basically fully finance it and pay for it. Even if you make a lot of money already, this is typically paid for. And where can you work with this degree? I already said it, but typical places you would work is airliners, for example, Alaska, Delta Airlines, United Airliners, people who work in the airports and give airplane services are aviation mechanics. Or you can work for manufacturers like Airbus, Boeing, or NASA, or anyone who builds things that go fly. So if you've got questions about this program, talk to me. I don't have this degree, but I can point you to the right people. And so today's presentation, the key takeaway is flight is about balancing forces, that the 4 forces we talked about. There are multiple disciplines that come together, engineers and non-engineers, to make it possible. Testing is one of the most crucial areas in the aerospace industry to make sure safety is met. Safety is crucial. When you are doing and making decisions and you're doing testing and you're working in the industry, you're affecting other people's lives. And having a safety mindset is crucial because you do not want to be the person who made a decision and because of your decision, an airplane crashed and killed multiple people. You don't want to be that person, but also don't be too scared. What you're going to be doing is cool. You're going to be learning a lot. And you get to say, I worked on that airplane that continued flying for the next 30 years. So it is crucial. It is very important that you have the safety in mind and you have, the heart to build stuff. And so there are many career paths in this industry. And it's not just for engineers. It's not just for technicians. It's for everybody. It's open to everybody. If you are not an engineer, or a technician, and you still want to, get a job in this industry, there's a place for you. And with that, I'll take questions. Thank you.
This marks the end of our presentation. Thank you for listening, and if you would like to learn more or get in touch, please visit us at somalieNgineers.org.